Here I have air, and it's compressed adiabatically from a pressure and temperature to a pressure and a volume as shown here. Okay, we'll assume it's an ideal gas behavior. We're going to ignore kinetic and potential energy. I want to calculate the work for this process. Okay, and I want to do it two ways. One, my preferred way, using table A22, and the second, using constant specific heat evaluated at 300 Kelvin. So we'll take it the first way first. Okay, the table A22. Now I'm going to use my first law equation here, which is again delta U equals Q minus W, where Q is 0 because it's adiabatic. So by definition, that's 0 heat transfer. Okay, so from this, I know that my work, I guess work divided by mass, is U1 minus U2. And again, that's because of the negative sign. Instead of U2 minus U1, I get U1 minus U2 to get the work of this. Okay, so what I'm looking for is the change in energy. So I'm going to find the energy using table 1. Do that first. So in order to find that, remember that energy only depends on temperature. I know temperature 1 is 300. So all I need to do is find temperature 2, and I can look up the U value for that. Okay, temperature 2 I'm going to find from my basically PV equals RT equation, right? Because it's an ideal gas. Okay, so if I want to find temperature 2, okay, that's going to be P2, which is 15 bar, which is 15 times 10 to the 5th. The volume is 0.1227 cubic meters per kilogram, okay, divided by R, which is 8,314 joules per blah, blah, blah in kilomoles, divided by the molecular weight of air. And you're going to see this many, many times. You can look it up in table A1, but the molecular weight of air is 28.97. Okay. So from this, I can find that my temperature is 641 Kelvin. So using this temperature and this temperature, I'm going to look up basically U1 and U2 in table A22. So here's table A22. Oops, that's the wrong. We're in metric. Okay, it's all based on temperature. So again, I go to 300 and I see my U value is 214.07. And then for 641, okay, you'll do the interpolation. It's just a little bit above 565. It's in between 465, excuse me, and 473. And what I actually get is 466.5 when I do the interpolation. Again, I'm at 641, so I'm 1/10 of the way between these two. Okay, so again, from that table, I find that the U value is, again, 214.07 for U1, and U2 is 466.51. Throwing that into my equation up here, I get 214.07 minus 466.51 equals negative 252.4, and my units on this are kilojoules per kilogram. Now this is the answer I would prefer that you get. I'd rather you use the tables. This is more correct than the way I'm going to do it now, which is stating that we're going to use a constant specific heat evaluated at 300. So again, now to find this second part, maybe I'll draw a line here. Okay, I'm going to use U1 minus U2 is going to equal CV times T1 minus T2. Now again, I know T1 is 300. I know T2 is 641. I just need to evaluate what CV is, okay, at 300 Kelvin. So I'm going to use CV. I'm going to actually find this. There's a table here, A20, which gives me the specific heats for some constant gases. Now, for air, again, CV is right here, and you can see as my temperature increases, my CV also increases. So this assumption that the specific heat is constant is not a good assumption. It changes as a function of temperature. However, the problem explicitly told me, hey, use CV at 300 and assume it's constant, which it is not constant. It actually goes up to about 0.77, you can see, from 0.718. But we'll use this 0.718 to calculate the answer as the problem asked me to do. So CV is 0.718 as I look up in the answer there. That gives me 0.718 times the change in temperature again, which is going to be 300 minus 641, which gives me a work of negative 245 kilojoules per kilogram. So we solved it both ways, but you'll notice there is, what is that, 7 off, about a 3% error between the two values. Okay, and the bigger that temperature change gets, the bigger the error is going to get. Okay, this assumption is not a good assumption. This assumption is the better assumption. This is the better answer. I want you to use a table if you have it. Only use this constant specific heat if the problem explicitly states